Previous videos have explained the concept of healing, and I've also discussed numerical examples explaining the concept of healing and how to involve or how to calculate numerical problems that involve that concept. This video will focus on the concept of list. So for those of you who don't know what is the difference between healing and listing, I have explained it in my previous videos, but I'll provide you with a quick explanation. So healing is caused due to natural elements like winds and waves, or even when the mooring ropes are too tight, or if a vessel makes a sudden alteration of course, or a large alteration of course, or a fast alteration of course due to the centrifugal force acting on the vessel kind of heels onto one side. So list or listing is the concept that involves the transverse inclination of the vessel or the ship caused when the center of the gravity of the ship is off the center line. So again, in this case also there's a transverse inclination of the ship, as is in the case of healing, but listing is caused due to the loading, discharging, or shifting of or unequal distribution of weights on the vessel. In healing, of course, because there is no weights involved, the center of the gravity doesn't shift, it's only the center of the buoyancy that shifts. But in listing, both the center of the gravity and the center of the buoyancy shift. Alright, so let's talk about listing today, and we'll also discuss a few numerical examples, and I'll show you how to solve calculations that involve this concept. But before I do that, I just want to show you a bit of a theory here to give you a theoretical background of this concept. So the first example here is figure 1, is showing a vessel that is completely upright. For a vessel is upright, and in this case the center of the gravity and the center of the buoyancy are acting in equal and opposite directions, and they're cancelling each other out. In this case, a vessel is in static equilibrium, where the force of the gravity is equal to the force of buoyancy, denoted by G and B respectively, and the center of the buoyancy and the center of the gravity are in a vertical line. In figure 2, which is this figure here, due to asymmetric loading or unequal loading, discharging, or shifting of weights, the center of the gravity is moved out of the center line, because of which the consequence or the resultant of that action is that the ship will sink or rise as necessary until the force of gravity equals the force of buoyancy. Alright, but it also means, and as shown in figure 3, if you see this figure here, you can see that there is a transverse inclination of the vessel. So the forces of buoyancy and gravity will form a couple which will cause the ship to incline until the center of buoyancy comes vertically below the center of gravity. In this case, GG1 becomes the transverse shift of the center of gravity, as you can see above. Alright, the couple formed by the forces of gravity and buoyancy causes the ship to incline or transversely incline as the center of buoyancy shifts to the lower side, and when it comes vertically under G1, which is the new center of gravity, the ship would be in static equilibrium. Static equilibrium means the couple can bring the ship back to the upright position as well. The angle at which the ship reaches its static equilibrium is the list, which is denoted by phi or theta. So tan of theta is denoted by GG1, which is the transverse shift of the center of gravity, divided by GM, which is the GM fluid before listing, or GM final before listing, not fluid but final before listing. But because GG1, or the shift in the center of gravity, is also calculated by distance moved between the weights and the weight moved, which is denoted by small w divided by displacement, tan theta can also be written as dw by w, which is equal to gg1. So this equation is equal to gg1 by gm. So d by w, here d is the distance the weight moves, loads, or discharge, so shift in the center of gravity. Weight or w is the weight loaded, discharged, or shifted. Loaded, discharged, or shifted. But the big W here is the displacement. Alright, So if I go back to the drawing here, you can see here and that in figure 3 the vessel has listed onto the one side, the center of gravity has shifted, and so has the center of buoyancy. The new center of buoyancy becomes the geometric center of the new underwater volume, the immersed part of the vessel. Alright, M here is the transverse metacenter, and the angle at which this happens is the list, denoted by theta. The formula for calculating list is tan theta equals gg1 by gm, where gg1 is the transverse shift of the center of gravity which occurs due to unequal or asymmetrical loading, discharging or shifting of weights. But gg1 is also equal to dw by w. Now if you don't know why this is, watch my video on kg calculations and you will understand what it is about. So that's why this is video 10 in the series of ship stability. I'll provide you with the links to the previous 9 videos in the description section below. I advise you to watch those videos in order before you watch this video here, because there will be concepts here which I'll assume that you know about, and if you are not familiar with those concepts, it's advisable for you to watch those videos first before you start watching this video. Alright, so gg1 in the formula above can be replaced by dw by w, and that's why tan theta is also equal to dw by w and also gm multiplied by gm in the denominator section here. So let's take a couple of examples here to explain the concept of how to calculate the list, or if the list is given to you, how to calculate the other components of the formula. So here is question 1 and solution 1. So question 1 says that on a ship of displacement 5000 tons, so W denotes the displacement, GM is 0.8 meters, 40 tons of cargo is shifted transversely by 10 meters. Find the list. So I've started off with a very simple example here just to explain to you the concepts of the formula here to calculate the list. So the formula for calculating the list is tan of theta, where theta is the list of course, equals d by w divided by w by gm, where dw is the transverse shift of weight. In this case, the weight has been transversely shifted by 10 meters. The weight shifted is about 40 tons. Since the displacement has not changed, the cargo has only shifted, the cargo has not been loaded or discharged, so the final displacement remains the same, which is 5000 tons, and the gm is given to you in the question as 0.8. So if you put these values in the formula here, tan theta will be equal to 0.1. Take tan to the other side, makes it tan inverse of 0.1 is 5.7 degrees. So the final list is 5.7 degrees if 40 tons of cargo is shifted transversely by 10 meters on this vessel. Let's take question number 2, which will be a different question here. In this question number 2, the ship's displacement is 10,000 tons. Km of the vessel is 7 meters and kg is 6 meters. The following cargo work was carried out on this ship. The vessel loaded 800 tons in number 2 lower hold, where kg is 3.75 meters. 4 meters to port of the center line. This is the first operation carried out. The second operation was the cargo loaded was 600 tons in number 4 lower hold, kg was 6 meters, and the cargo was loaded 8 meters to starboard side of the center line. The third operation was that the cargo of 400 tons was discharged from upper deck, kg 10 meters, and it was done from 2 meters to the port of center line. If our free surface moment is 4400 tons meter, find the final list. I'll tell you what free surface moment is as we go below. So then you need to summarize all these operations in a few columns. So let's start with, let's find the final listing moment. So we are trying to find the list here, right? You have to find the list. To find the list, you have to find the final listing moment after the cargo was loaded and discharged. Alright, so in the remarks column, put where the cargo was loaded or discharged from. Then you have the weight column. Under the weight column you have the loaded and the discharged columns. Right, put the weights loaded and discharged, summarize it. Then make a column for distance of the center line. So this will give you an idea from where it was loaded or discharged. So if you load it on the port side, as it was in the first case, the vessel will list to port. If you discharge from the port side, the vessel will list on the opposite side, that is starboard side. So in the first case, 800 tons was loaded on the port side, 4 meters on the port side. So the listing moment will be towards port because you are loading on the port side. So the listing moment on the port side will be calculated by 800 multiplied by 4, 800 multiplied by 4, which is equal to 3200. In the second case, the 600 tons was loaded on the starboard side, because of which the listing moment will be towards starboard. So the final listing moment on the starboard side will be calculated by 600 times 8, which is equal to 4,800. The third one, the 400 tons was discharged. 400 tons was discharged, but from the port side. If it's discharged from the port side, the vessel will be listing towards the starboard side, because this is a discharging, not a loading. When you discharge the cargo is off the ship, the vessel will list onto the opposite side, and that's why the final listing moment is towards starboard in this case, because the cargo was discharged from the port side. And you calculate it by multiplying 400 tons of cargo multiplied by 2 meters, which is equal to 800. So the summarized port listing moment is 3200 and starboard is 5600. So more listing moment is towards starboard side. So your resultant final listing moment will be 5600 minus 3200, which is 2400 tons, but this is towards the starboard side. So you might write starboard here because that gives you an indication of where the ship will be listing at the end. But if you go back to the formula, to calculate the list, you also need the GM. Alright, so how can you find out the GM? To find out the GM, again summarize the information here. So make a remarks column, make a weight, loading and discharge column, write down the kg, and then you can calculate the moment by keel. So this is the vertical shift of the center of gravity. The previous one was a transverse shift of the center of gravity. So to calculate the vertical shift of the center of gravity, you also have to include the ship's displacement. The kg was 6 meters. So moment by the keel will be 60,000. 6 multiplied by 10,000. That is the displacement is included in the moment. Then number 2 hold, 800 tons was loaded. That is also becomes part of the displacement of the ship. So if 800 tons is loaded and the kg was 3.75, multiply 800 by 3.75, you will get 3000 tons, and you put it under the moment of loading. Number 4 hold, also 600 tons was loaded, becomes part of the displacement. You will calculate it as 3600. And finally, from the upper deck, 400 tons was discharged. This is no longer part of the displacement. It will be subtracted from the total displacement. So you will put it under the discharge column of 4000. So 400 times 10 is 4000. So total displacement is 66,600. Then you subtract 4000 because 400 tons was discharged. So from the moment by the keel, 4000 will be subtracted of the loaded moment. So your final displacement becomes 11,000. Your moment by the keel becomes 62,600. So your final kg, and this is a vertical shift of the center of gravity, will be 62,600 divided by the final displacement of 11,000. So your kg or vertical kg or final kg will be about 5.691 meters above the keel. So your center of gravity is about 5.691 meters above the center of the keel. To calculate your free surface correction, you have your free surface moment divided by the displacement. The free surface correction, free surface moment is 4,400 given to you already. The free surface moment refers to the slack tanks on the ship. Any slack tanks on the ship are they contribute to the free movement of the liquid in that cargo or in the tank, and that creates a free surface moment. So if our tanks are slack, they are not full, the tanks will move, the liquid in the tanks will move. It could be cargo or it could be ballast water. Due to this shifting or the moving of this cargo or ballast water, the center of the gravity may also shift. So you have to calculate that as well. So the free surface moment of 4,400 is given to you. You will divide it by the final displacement of 11,000, and that gives you a free surface correction of 0.4 meters. To calculate your final GM, start with your km, subtract your kg to get your GM solid. km is given to you in the question. Kg is something you have calculated from here. Free surface correction is here. Free surface correction is always subtracted from GM. So when you subtract km and kg, you get GM solid. This S is solid, GM solid. You subtract the free surface correction. Always subtract the free surface correction. You get the GM fluid or the final GM, which is 0.909. To find the list, you have to use the formula final listing moment, that is shift in the weight of the cargo. So this is a resultant. So when only one weight is involved, you write d by w, but when multiple weights are involved, you will write listing moment, because you have to find out the resultant listing that takes place due to the shifting cargo loading or discharging. This 2,400 is the final listing moment. So 2,400 is from here that you calculated here. That is the transverse shift of the weights. Alright, so that is from above, and then you divide it by displacement by GM. GM is the final GM that you calculated just above. So you will get tan theta equals to 0.24002. Take tan to the other side. You will get tan inverse of the value, and you will get the final listing here as 13.5 degrees. This is the final list. So remember, when there is cargo loading, discharging or shifting, and you're calculating the list, you have to not only consider the transverse shift of the weight, but also the vertical shift of the weights. So the transverse shift of the weight is the listing moment, and the vertical shift of the weights and vertical shift of the center of gravity is calculated as moment by keel. Alright, so you have to consider both. So when it's moment by keel, you have to consider the final displacement, include the ship's displacement in it. But when we're talking about listing moment, the ship's displacement is not involved in it, because the ship's list does not depend on the ship's displacement. Alright, but when it comes to the vertical shift in the center of the gravity, the ship gets involved because there is an original center of gravity involved in it. Alright, let's take the final example for today, and this is question number 3, in which the ship has a displacement of 16,000 tons. The km is 9 meters, kg is 8 meters. The vessel is listed 7 degrees to starboard. The following cargo tank or cargo work takes place on this vessel. The first one is, the vessel loads 1600 tons of cargo at a kg of 4.5, 5 meters to port. The vessel also loads 1400 tons of cargo, kg of 8 meters, 4.5 meters to starboard. The vessel also discharges 1000 tons of cargo, kg 6.5 meters, and it is done from 1 meter from starboard. You have to find out how many tons of ballast water must be transferred transversely to upright the vessel if the port and starboard tank centers are 10 meters apart. So remember, the vessel here is already listing 7 degrees to starboard, and then you carry out certain cargo operations. So you have to again calculate the shift in the center of the gravity due to these cargo operations, and then add to the original existing list of 7 degrees to starboard. So let's start with the solution here. Remember, the vessel is required to be upright, so your final listing moment must be 0. Since final kg is not asked here, you need not be calculated. To find the final listing moment, remember tan theta equals dw by w by gm. That means dw will give you the initial listing moment. You need this initial listing moment because you need to now add to the initial listing moment of the other cargo operations that take place, and that will give you the resultant listing moment. So because the vessel is already listed 7 degrees to starboard when you start this question, you will find out the initial listing moment. Alright, and then see what impact does the new cargo operations has on this listing moment. Does it counteract for it, or does it add more to it? So vessel is listing 7 degrees to starboard, remember that. So in this case, because tan theta equals dw by w by gm, you transpose the formula here. So initial listing, take w by gm here, because w, that is displacement, gm and tan theta is given to you. So your initial listing moment is 1964.6 tons meter to starboard, because the vessel is listing to starboard at the beginning of the question, right? So when you are summarizing the operations here, you already have an initial listing moment of 1964.6, right? Then you carried out the cargo operations. You loaded 1600 tons, 4.5 meters to port, which gives you a port listing moment. You load 1400 tons on 1 meters to starboard, which gives you a starboard listing moment. And finally, you discharge 1000 tons, and again I should have written, so 1000 tons was discharged 1 meter from starboard. So 1 meter, I have written it in the wrong order here. So 5, 4.5 and 1 meters to starboard. So this should be the other way around. So 5, 4.5 and 1 meter. This is starboard side. Right, this is starboard side again, and this is port side. Alright, so because you discharge 1 meter from starboard side, the listing moment will be towards port. Alright. So the final listing moment will be 9000 on the port side. So just add these, and then 8264.6 on the starboard side. The resultant listing moment, port minus starboard, so 9000 minus 8264.6 will give you a final listing moment of 735.4 to port side. So although you started off with a listing moment of 1964.6 on the starboard side, due to the cargo operations that took place after that, you have now a listing moment of 735.4 to the port side. To upright this vessel, you are required to cause a listing moment of 735.4 to the opposite side, which is the starboard side, by shifting ballast water through tanks which are 10 meters apart. So that means you have a listing moment of 735.4 that you need to correct. You have a distance of 10 meters to move this weight, but the weight is unknown. So to correct 735.4 of listing moment, you need an opposing listing moment of 735.4 onto the starboard side. So you need to move the cargo from port to starboard, or you need to shift from port to starboard the ballast water, or you need to load it on the starboard side, alright, on the opposite side, to correct the list. So therefore, if the tanks are 10 meters apart and you need to shift the water from port to starboard, and you have to shift to correct a moment of 735.4, you will divide the distance by the total listing moment required, and that will give you the weight of the water that is required to be shifted from port to starboard. So in this case, the vessel was listed onto the port side. The final listing moment was 735.4. When I shift 73.54 meters here from port to starboard through a distance of 10 meters apart, so this distance will be 10 meters apart. Because of the shifting of the weight, the starboard side will also get some water now, and the port side will lose some water after the shifting, so the vessel will then become upright. Alright, so remember that when it talks about listing, we talk about the listing moments, and that's a transverse shift of the weights. But if you are anytime required to calculate the GM or the kg, you also have to take into consideration the vertical shift of the center of gravity. So I hope these different examples explain the concept of the transverse and the vertical shift of the center of gravity well. If you have any questions, please feel free to write in the comment section, and I'm happy to address those questions. I'll see you soon with my next video, and I'll give you a description to all the previous videos in the stability series in the description section of this video below. Thank you for watching, and thank you for subscribing. I'll see you soon.